Now, in this chapter, we continue our study of objects, in particular, how we go about constructing, initializing, and using objects. All right, so here we have a class. Now, this is not a complete program. It's missing the class that has the main method that creates a initialize one object. All right, but anyway, what I want to focus on is how it initializes its instance variables. We have two instance variables. Line 3, we have x and y. Those are two instance variables. Line 5, we have the beginning of the constructor for this class. And what it does is it just initializes x to 0 and y to 1. Now, line 7 actually is unnecessary because the default value, if you don't, when you declare an instance variable, if you do not explicitly specify an initial value, it defaults to 0. So if you didn't have that constructor at all, x and y both would be initialized to 0. So x would be the way you would have the correct initial value. Y would not if you want y to have 1. So line 8 would be necessary, but not line 7. However, it might be a good thing to explicitly initialize x in the constructor, even though you don't really need to do that in this case, because then it makes clear what the initial value is. Someone might be looking at the program. If you didn't have that constructor, someone might be looking at the program and not know that x has an initial value of 0, and therefore they would not be able to understand the program. But when you explicitly initialize x, then it's clear what the initial value has. By the way, you notice that the data, the instance variables in this class are private, and that's normally the case. You want them private, so someone from outside the class, some program, some part of some program cannot go directly to X and Y and start modifying them. You however, can get to X and Y via the public methods. So line 11 is a public method that can access X and Y, but you can't access X and Y from outside the class. As I said, this is normally a good feature because you want the uh, the interaction with the instance variables through methods that are in that class. And those methods were specifically designed to correctly work with the instance variables. If, however, X and Y were public, then someone outside might use the instance variables in some incorrect way, right? So, for example, let's say, um, you had a class that had temperature, weather temperatures, and and let's say you could set the temperature anything you want. If you invoked a method to set it, let's say to 20, um, then it would set the temperature to 20. But let's say you use that method to try to set it to 20 billion. Obviously that would be a mistake, and so that method would detect it and then notify the programmer that there's a user rather that is an incorrect use, incorrect temperature to assign. But if the temperature instance variable were public, then someone could change the temperature to 20 billion, and there would be no notification when the program is executed, because 20 billion, not 20 billion, let's say actually 20 billion would what would be an interesting experiment for you to do is write a program that has an int variable, for example, x, and then assign it 20 billion and see what happens. See, that's outside the range of an int variable. An int variable ranges from -2 billion to +2 billion. So 20 billion can't fit in there. So on the other hand, it may be that that's not going to be viewed as an illegal instruction because 20 billion is an int. It's an integer constant. Well, it actually isn't. It's a long constant. So I don't know what's going to happen there. You might want to try that and just see how that works. Do you get an indication when you assign to an integer a value which is outside its range? It might just chop it off. That might happen. You might not get any indication that that's illegal. But I think it's going to be illegal, and this is why. Remember the rule that you can have the left-hand side and the right-hand side different types, but the left-hand side has to have a bigger range or equal range to the thing on the right in an assignment statement. So if you have 20 billion, that's type long. And if x is int, that's type int. Now, int has a shorter range, a narrower range than something of type long. So if we use that rule, that you can't do that, if we apply that rule as we currently know it, then that should be triggered as illegal. And you won't just have the 20 billion truncated so that it can fit into the int. Anyway, try that and see what happens. I off the top of my head, don't know the answer to that. All right, anyway, that's an interesting question. So that's the typical setup for a class that is going to, from which you're going to create objects, is that the instance data is private and the methods that work with that instance data are public. And so that forces someone who's using the object created from that class to go through the methods in order to work with the instance data. And those methods will have checks in them so that it ensures that the data is always valid. It's not going to have some crazy values in it, which would be possible if the instance data was public, which means that someone could from the outside go into them and set them to anything whatsoever, even though it might be totally absurd. All right, now, if a instance variable is not initialized, then it defaults to 0. You see byte, short, int, long, float, double, even char will have 0 in it. Boolean is initialized to the value false, and a pointer to a class, like let's say you say string s, all right, where you precede the variable identifier with a class, then that's called the class variable, and it's a pointer. That's how you get pointers that can point to objects. Anyway, if you don't initialize it, if you just say string s and you don't say equals, some string, so you don't initialize it, then that pointer is initialized to the null pointer. Now, what is the null pointer? It's a pointer, it's a valid pointer, but it doesn't point anywhere. That's the null pointer, right? It's a pointer. You can assign the null pointer to a pointer, right? Because the null pointer has the type pointer, but it doesn't point anywhere, right? So those are the default initial values. And as I said, you may not want to really take advantage of the fact that you have these defaults, because then someone reading your program may not realize that in x, where x is a instance variable, is since you're not giving it an initial value, is in fact have initial value. They may think, oh, it has no value, it has garbage, you have a bug in your program. So they may be sent off on a wild goose chase because because that person may think it doesn't have any initial value. Now remember, when you declare a local variable, that's a variable within a method, it does not have any initial value. It doesn't have a default value. It has a initial value only if you explicitly specify one. For example, if you said int x equals 1, all right, now it's going to have an initial value of 1. But if you just said int x, semicolon, then x has no initial value. It does not have 0. It does not have any initial value. Now, that's local variables. Those are variables that are declared within a method. An instance variable, as well as static variables, as you know, are declared outside methods, within the class, but outside methods. All right, now here I'm just saying why explicit initialization may be better. And I already mentioned number one there that not everybody knows about the default values. And so it may be clearer, your program may be clearer, easier to read, easier to understand if you explicitly initialize your instance variables. And then number two is also a second reason, but I think it's very unlikely that Java at some point, some future release of Java is going to change the initial values instance variables have, the default initial values they have. However, it's not inconceivable. And if you explicitly initialize, then the initial values are still what you want. But if you rely on default values, and the default values at some point in the future are changed by the creators of Java, then your program no longer works correctly because it won't have the default values that you want. But either way, from my point of view, is fine. You know, when I write programs, I generally take advantage of the initial default values because that means I have to type in less. You know, I don't have to say equals 0. All right, now, yeah, just to emphasize Z, what I've just said, Z is a local variable. And a local variable is declared within a method. So in this example, Z is inside F. So this is not an instance variable, it's a local variable. And this program is not going to work. If you have this method in a program, it will not work. F will not work. Why? Well, because Z does not have any initial value. And then if you try to do a print line on Z, there's nothing to print because there is no value in Z. So you'll get an error indication for that statement, the print line of Z. All right, so one way to initialize, explicitly initialize instance variables is to put the initialization right in the declaration statement. So here we are specifying an initial value for y of 1. So that's one way of doing it. And x in this example is going to have a default initial value, which is 0. So if you create an object from this class and then you call display sum, it's going to display the sum of x and y, and the sum, of course, is 0 plus 1, which is equal to 1. So it will display sum will just display 1. All right, now let's see. If you use the constructor to initialize instance variables, then the class is more flexible. So here I parameterize the constructor initialize3, right? The class name is initialize3, so on line 4, that's the constructor, and I parameterize it. It has 2 parameters. So in the main method, when I'm constructing an initialize3 object, you know, I say new initialize parentheses 10 comma 20. So 10 and 20 are going to be assigned automatically. Those are the arguments that correspond to the 2 parameters here, xx and yy. So xx receives 10, yy receives 20, and then those 2 values are assigned to the instance variables. So x, the instance variable, will initialize to 10. The instance variable will be initialized to 20. All right. But let's say we want to create an object from initialize3 which has 1 and 2 in x and y. Well, that's very easy to do. In main, when you're creating the object, you say new initialize3 parentheses 1 comma 2. So when you construct the object, you are determining the initial values. Whereas in the previous example, you're stuck with whatever initial values were specified in the declaration statement. So there's much more flexibility. So constructors generally, probably more often than not, use this, use the parameter, more often than not, you have constructors that are parameterized so that when you construct the object, you can specify what the initial values are for your instance variables. For example, the constructor for a scanner class. Remember, we specified the argument system.in, which represents the keyboard. So the constructor for the string class is you can control where that scanner is going to read from. If you pass when you construct a string object, if you pass it the system.in, the scanner object will read from the keyboard. But if you pass it something that specifies a file, you read from a file on your hard disk. All right, so that's common that you parameterize the constructor, and that way when you construct the object, you can specify the initial values of your instance variables. All right, now here is a very simple example, and we have a method called change, and we have some code at the beginning here. Let's assume the code at the beginning is in the main method, and this change method is also in that same class that contains the main method. So you have a class that has the main method that contains the stuff at the top, and then you also have this change method. So let's see what's going to happen when main's executed. It's going to execute those statements at the top. P will be created and initialized to 1, and then you call change passing it P. So the computer determines the value of P, which is 1, and that 1 is automatically assigned to corresponding parameter in change, which is Q. If you look down at the bottom, you see that the parameter that corresponds to the argument P is Q. So Q will receive 1. So when you call this thing, you're going to get the Q created, the Q parameter created, and it, like P, will also have 1. Both of them will have 1. But then if change assigns Q to 2, if it assigns 2 to Q, then Q changes, but that has no effect on P. Why should it? Q is a separate slot. You're changing the value in Q, so there's no reason why P should suddenly change. Okay, so the important point here is that when you change a parameter like Q, it does not have any effect on the argument. So when you change Q here, which is the parameter, it has no effect on the argument in the calling statement, which is P. So you change Q, it doesn't change P. You change the parameter Q, it doesn't change the corresponding argument P in the calling statement. All right, pretty simple observation. Okay. Now, if you didn't study Java at all, you might think, oh, if you change Q, it's also going to change P, but that's not how it works. If you change Q, it has no effect on P because Q is a separate box in memory from P. Now here we have a class, and it's part of a program. I'll show you the rest of the program in just a second. And it has an instance variable which is initialized to X. But you also have a xset method which has a parameter X, and when you call xset, you pass it some value like 20, which is assigned to XX, and then the XX, the value in XX is assigned to X. So although X has an initial value of 1, you can change it anytime by calling xset and passing xset, the new value you want X to have. And then xget will just return whatever is currently in X to whomever is calling xget, right? You see on line 10, you have the return type there, ints, and return X. So it's going to return an integer, therefore preceding the the method name, you need the correct return type, which is not void, right? It's int. And notice the two methods that work with the instance variable x are public, but the instance variable is private. As I said, that's the normal way classes are set up. So you cannot access x directly. You have to go through either xset or xget. By the way, xset, because it changes a instance variable, sometimes referred to as a mutator method. Mutate means change. So a mutator method is something that changes the instance data, instance variables. And xget is called an accessor method because it allows you to access the values in instance variables. So we have mutator method, which is xset, and xset, and a accessor method, xget. All right, so let's take a look at the rest of the program, which is on the next slide, I believe. All right, so here we have the rest of the program. It's in a class called test side effect, test side effect. And let's see, the main method starts out by initializing p to 1, and then it calls change, passing it p, and there's change. Then it's the second method. It's the change. We got two change methods, by the way. Is that legal? Well, yeah, because you can overload method names. Remember that from a previous chapter? But the methods have to be distinguished by the parameters. The parameter lists have to differ in either order, number, or type. So they have the same number, right? And there's only one, so they both have the same order, but their types are different. For the first change method, you have type int, and for the second one, you have type side effect. So T is where, you know, the parameter there is a pointer to an object whose type is side effect. All right. All right, so when we call that first change in the main method, we're passing an int, so we're going to call so the compiler will interpret that as a call of the change that has an int parameter. And that one will just assign q to 2, and of course that has no effect on p. Then when we go back to main, the q goes away. So that whole procedure there, you know, was for nothing other than just explaining how things work with respect to arguments and their corresponding parameters. But now we have something different happening here. We're calling, let's see, we're calling the constructor. We're using new to construct a new side effect object. And that following new is the call of the constructor. And so we get a new side effect object, and the pointer to it is assigned to R. And now we call change passing it R. Now what's the type of R? It's side effect, right? R is the side effect pointer. And so the method that is going to be called is the one whose parameter has the type side effect. So this second call of change is going to be calling the second change method. Now that second change method is not going to be able to change what's in R, right? Now in this case, the second change method is not making any attempt to change R. Let's say that second method there, the second change method, had the following statement: T is assigned null, semicolon. All right, it didn't have the statement that is there. It just had T is assigned null, semicolon. Now null is the null pointer, so we're assigning T the null pointer. Okay. But before we do that, T is going to have the pointer that was passed to it, by the call of change. It's going to have a pointer that is in R, right? When you call change passing in R, the value in R, that pointer is passed to T. So T, when you first call it, has a pointer to some object, a side effect object. But then when you say T is assigned null, semicolon, that what's in T gets changed. It gets changed to the null pointer. Does that have any effect on R? No, it doesn't, because T and R are separate slots. So you cannot change a pointer, a pointer argument by changing the corresponding pointer parameter. All right? Okay. All right, now let's get back to the change method as it actually appears in this slide. So the change method, who's the second one, whose parameter is side effect, then does the following. It calls xset, passing it 2. Now, which xset? You could have many xsets. You could have many side effect objects. So you have to specify which side effect objects. You have to qualify it with the pointer. So that's what we're doing. So we are going to change by calling xset. We're going to change the x instance variable in the object to which t points to 2. All right, we're going to change it to 2. So if you recall, if you think back to the side effect class that we were just looking at it, x initially has the value of 1, I think, right? So we're going to change it. All right, so change cannot, no matter what you do, it cannot change the value of R, but it can change what R points to. This thing here, because T receives the pointer that's also in R, and then we're using T to qualify this call of xset. We are actually changing the x variable in the object to which R points. So we can't change R, but we can change what R is pointing to. And this is called a side effect, right? We're not changing R, but we're changing what R points to. So it's a side effect. It's an effect that we don't apparently don't have any change in R here, because R corresponds to T and they're two separate slots, but a change actually is occurring, and it's occurring in the object to which R points. So the whole structure associated with R can change, specifically the object to which R points, but you cannot change R by changing T in the change method. Okay? So that's a big difference between passing a primitive value like an int and passing a pointer to an object. The called method is not going to be able to change that reference variable in the calling statement, but it can change the object to which it points, and that's called a side effect. All right, so yeah, this is just another thing to explain what I've just been explaining. So here we're creating a new side effect object, and the pointer to it is assigned to R. Then we're passing R, and then we're calling xget. Oh, we're calling xget. Oh yeah, okay, here. So this is what's going to happen. This is an interesting sequence here. So we have this R, which is pointing to a new object that we create with this first statement here. And this object has 1 in x. It has an instance variable x, which is initialized to 1. Then we call change R. So we're passing R to the change method, which is shown on this side. So R is received by T. So both R and T, they're separate slots. They both point to the same object, the one that the first statement created, that has 1 in the x instance variable. And then when we call xset, the x set in the object to which P points, that of course is the x set in the object to which R points, because R and T point to the same object. So that's going to change the x instance variable in the object to which R points. So we're not changing R, but we're changing what R points to. Yeah, so here we have R, and when you make that call, T receives what's in R. So both R and T are pointing to the same object. And if you were to execute in main, R dot x set, some value, or T dot x set, if in the called method, the change method, you say T dot x set, in either case, you're going to be changing the same object because both R and T are pointing to the same object. All right, now we're going to look at a different kind of constructor. It's called a copy constructor. Now, if you look at this class con1, you'll see that it actually has two constructors. And as you know, a constructor has to have a name identical to the class name. So you'll see on line 5 a constructor, con1, and line 10 a second constructor, con1. And this is legal because those two constructors are distinguished by their parameter lists. On line 5, the parameter for that constructor is type int, and for the one on line 10, its type is con1, which means original is going to be a pointer to a con1 object. Okay. Now, the effect of the constructor that starts on line 10 is to make a copy of the object to which it's passed. So when you call that second one, you're passing it a pointer to a con1 object, and it makes a copy of it. So you have two objects that are identical. All right, so let's see how this thing works. On line 20, we are creating a new con1 object. The parameter is the parameter is 5. No, the argument. That's the argument. The argument is 5, and so we're going to invoke the constructor that starts. It just coincidentally starts in line 5. The constructor that has an int parameter. So it just coincidentally is the one that starts on line 5. Okay, if we had con1 15 in there, we wouldn't start on line 15. We would still go to line 5. All right, so anyway, and that 5 is assigned to XX, which is then assigned on line 7 to the instance variable X. All right, so as a result, and then the pointer to this new con1 object is assigned to C1. So C1 points to a con1 object that has in its X instance variable 5. Okay. Now, we then execute in main line 21, which also creates a new con1 object, a second con1 object. I'm going to call the first one the original one, and the second one, which we create on line 21, the new one. Okay. So the new triggers the creation of a new con1 object, and then then the computer, does the invocation of the con1 copy constructor, but this time it's going to execute the one that starts on line 10, because the type of C1 is con1, and the type of the parameter on line 10 is also con1. So they have matching type. So obviously that's the one that the computer is going to use. So we're passing what's in C1 to the parameter original on line 10. All right, so original is pointing to the original one, the first one, the one that I created on line 20. All right. And then on line 12, we do an assignment statement. Now, what is original.x? Well, X is a instance variable, and original is a pointer to the original object. So original.x is the X field, right? We're qualifying X with a pointer to an object. So that's going to access the X in the object to which original points, which is the first one, the one I created on line 20. All right. And then that right-hand side of that assignment statement on line 21 is going to return a pointer to this second object, which is then assigned to C2. So C1 points to an object, C2 points to a second object. The two objects are identical. The constructor at line that starts on line 10 copied the original one. That's why it's called a copy constructor. And this is the result. We have C1 pointing to a Con1 object that has an X field. It also has some methods in it, of course, the X field. And C2 is a copy of that one, which has an X field, has an X instance variable, which has 5 in it. All right, so that's pretty simple. However, there's a little complication that can occur when you're implementing a copy constructor. There's no complication if the instance variables are just primitive, have primitive type, like ints. For example, in this example, the instance variable was type int. But there is a complication if the instance variable is a pointer, an object pointer. So let's say we have a Con2 object, and its instance variable R has an instance variable R, which also is a pointer to an object, but a different type of object, a D object. And when we create the first Con2 object, that will create a D object and put the result in the pointer to it in R, and then the constructor, when we're constructing the Con2 object, is assigned to P1. So we have P1 pointing to a Con2 object, which in turn points to the D object. Now, if we have a copy constructor and we just simply do what the previous example does, is just make a copy of the instance variables, this is what we're going to get. The after picture here is what we're going to get. So if we call a copy constructor that just takes the pointer, which is in R for the original object, Con2 object, and place it in the R field of the new one, we get a second object, right? But the R fields will point to the same D object, right? Because you're just copying that pointer. Right? If you do exactly what we did in the previous one, you get this structure in which the two Con objects point to the same D object. Okay. So the two objects are not independent. Using P1, you could get to the first Con2 object, and then using R, you can get to the D object and make changes to the D object. But that's also going to change the P2 structure, because the P2 structure is also pointing to that D object. P2 points to the Con2 object, which in turn points to that D object. So if you use P1 to ultimately get to the D object and change it, it also changes the structure associated with P2, and vice versa. If you use P2 to ultimately get to the D object and change it, that changes the structure associated with the P1 pointer. And if you do this, it's generally it's not desirable to have this kind of situation. Generally, if we want a copy of an object, we want a copy that's completely independent, right? Completely independent. These two aren't independent. They share the same D object. So there is this connection between the two. Anyway, if you do have this situation where they're not completely independent, it's called a shallow copy. We're just copying. A shallow copy is you get when you're just copying the instance variable from the original ones to the corresponding instance variables in the new object which you're copying from the original one, right? So you just make a copy of the instance variables. So if the original instance variable is a pointer to an object, the copy is going to point to that same object as we have in this example. This is what we would like. Should be the correct. This should be the correct. This is the correct after picture. So we have this original con2 object. P1 points to it, and it in turn points to a D object. And then we make a copy of that original one, and its R field points to a separate D object, which is identical to the first one, but it's a separate D object. So these two things, those two structures are identical, right? Are identical, but they're completely separate. So if you use P1 to ultimately get to the D object and change it, it has no effect on the P2 structure and vice versa. And if you do that, if the copy is completely separate from the original, then it's called a deep copy. Okay? It's called the deep copy. Now, here is the version of Con2 class, which creates the shallow copy. So when you're creating the original one, you call con to the first constructor here that starts on line 5, and what it does is it creates a new D object, assigns it to R, and then the constructor then returns a pointer to that new object, which is then assigned to a pointer in main. Okay, and then if main calls the second con2 constructor, passing it to pointer to the first con2 object, what we have on line 12 is just a simple copy of the instance variables. Original is a pointer to the original con2 object. So the right-hand side of that assignment statement is accessing the pointer that's pointing to the D field, to the D object. In the original one, it's assigning that pointer to the R field in this new one. So the R field in the new one is pointing to the same D object as the original one. Well, we're just doing a simple copy, just like the original version, the original example where we were just copying infields. But infields is fine because the two are completely separate. You get a deep copy. But now, because con2 object has a pointer that points to in turn points to a D object, this does not work as we normally would want it to. It makes a shallow copy. Typically, we would want a deep copy. So how do we make a D copy? Well, you have to make some change to this statement here. We just don't want to copy. We just don't want to copy the R field, which is pointing to a D object in the original, to the R field in the new one that we're creating to the R field in the copied one, right? We don't want to do that. We have to do something more complicated. Now, what do we have to do? If you look at this slide long enough, I bet it's just going to pop right into your head what you need to do. Now, let's see. What do we need to do? We have to, well, if you look at that diagram we were just looking at where you had a deep copy, you have a second D object, which the copy is going to point to. You don't want the two con2 objects pointing to the same D object. So you have to construct a new D object, right? You have to construct a new D object. And in order to do that, you want to, let's see, and that D object can't be any old D object. It should be identical to the D object in the original con2 object that the original con2 object is pointing to, right? So after this whole process, you have those two structures identical, but you have two separate D objects. So what you have to do is you have to pass D, the constructor. On line 12, you have to create a new D object, and you have to call the copy constructor in the D object, assuming it has one. All right, you have to call the copy constructor. And you're going to pass it the D pointer from the original one. Well, where do you have the D pointer? Well, original is pointing to the original one, right? So original.r is the R field in the original one, which is the D pointer, which is the pointer to the D object. So what you do is you invoke the copy constructor for D, passing it the D pointer in the original con2 object. And that creates a brand new D object, which is identical to the D object in the original one. And then you assign that to R, which is the R, line 12, the left-hand side R. That's the R in the new one. So you have the R field in the new one pointing to a brand new D object, which is identical to the D object in the original one. And there you have the correct modification to line 12 at the bottom of this slide. R equals new D parentheses original.r. Okay, now I will admit this is confusing, but if it's not that bad if you just think it through very, very carefully, right? We're creating a new object and we're passing it a pointer to the one in the original thing. So we get a brand new D object, and then we assign it to R, which is the R in this new copy one. So we have, and then this constructor returns to, that whole mechanism, new con2, whatever, returns to main the pointer to this second con2 object, which is completely distinct from the original, but identical to. All right, so just go over this carefully a couple of times. And of course, you could only do this if the D class has a copy constructor as well. And if it also has a pointer to, let's say, an E object, then it has to have, a special copy constructor. You can't just simply copy the instance variables. But if it's just primitive data, you can just do that simple kind of just copy the instance variables, and that's sufficient for making a deep copy. Now here we have an example. Let's see. We have two constructors, two con3 constructors, and the second one is a copy constructor. And we have two instance variables. We have R, which is type string, and X, which is type int. And the copy constructor, which starts on line 12, just does a simple copy. So normally this means you're going to have a shallow copy, because the R field is going to point to the same object in the copy. The R field in the copy is going to point to the same string object that the original points to, right? Because you're just copying the two pointers. So the two pointers, the two R pointers, will necessarily point to the same string object. So you would think, well, that's not good, because now you're going to have a shallow copy. But in fact, you will have, and then to just continue, then you're just copying the X fields. That's primitive, so that's fine. That's not going to cause any problem with respect to deep copy or shallow copy. However, line 14, that seems to be a problem, because you're just copying the pointer to the string, so you're going to have the two R fields in the copy object and the original both pointing to the string object. Okay, but this is a copy constructor that creates a deep copy, and the reason why is that a string object is immutable. You cannot change it. So the problem that you could run into with the previous example, with the two con2 objects pointing to a D object, if the two con2 objects are pointing to the same D object, it's possible from the first object you change the D object, but then that would change the copy, right? Because can be an interaction between the two. Whatever you do for whatever change you make in the D object, which affects both of those copies, both the original and the copy. All right. But that's not the case in this example because a string object is immutable. You cannot change it. But you say, well, that's not true. I remember in, I think it was chapter 2, that we used the method in the string object called toUpperCase, and we changed the case to all uppercase. Originally, we had hello in all lowercase, and we had hello in, the result was hello in all in uppercase. But that's not what we did. What we did is actually created, if you go back to that, you might want to review that. That's very important. We called toUpperCase method, and what it does is it makes a new string object. It leaves the original string object alone with the lowercase. It creates a new one with the string in uppercase. So the original one is unchanged. The new one, however, has the uppercase version of the string. All right, so that is not an example of changing what's in a string, actually changing the string in a string object. You cannot do that. It is immutable. All right. So this first, going to our main method here on line 23, we're creating a con3 object, and we're initializing the string to hello and 7 to and x to 7. By the way, when on line 23 we specified the string constant, you'll get automatically the object that contains that string. Now that normally doesn't happen, but strings are so common that we have this special facility with strings. If you just specify in a Java program a string constant, like we're doing here on line 23, the object is automatically created that contains that string. And a pointer to that object is what passed to the corresponding parameter RR on line 6. So line 6, RR on line 6 receives a pointer to a string object that contains hello, and XX receives 7. All right, and then the assignment statements on line 8 and 9 initialize R and X so that R points to the object hello, the string object that has hello in it, and X contains the int value 7. All right, then on line 24, we call the copy constructor. We pass it M1. So we're going to execute the constructor on line 12, and it just simply copies the R and X field in the original to the R and X fields in the new one. So on line 14, original.R and original.X, those are the R and X value. That's going to provide the R and X values of the original. We just are assigning them to R and X, which is the R and X into the copy that we're constructing on line 24. But nevertheless, it's a deep copy. And why? Even though we're sharing this string object, it's a deep copy because this thing is immutable. This string object is immutable. So there's no way using M1 getting to R3 and then using R using M1 to getting into the con3 object there, and then using R to get into string. You can't change string. So they really have no potential, even though they're sharing something. There can be no interaction between M1 and M2. No matter what you do with M1, it's not going to affect the structure associated with M2, and whatever you do with M2 is not going to in any way affect the structure associated with the M1 pointer. Those two things do share a string object, but because the string object is immutable, all right, this still is a deep copy. All right. And I think that's the end of this slide. Let's see.